Hi there, and welcome to the video for section 1.5 on the topic of basis and dimension. Let's start here by recalling that in the previous section, we talked about the vector space Rn and subspaces of Rn. But remember, we can think of those subspaces as being kind of lower dimensional mini vector spaces, right? They're kind of smaller vector spaces contained in some bigger vector space. So typically a vector space has infinitely many vectors in it, but we describe them in terms of a finite set of vectors called a basis of that vector space. Just like how a plane and plane subspace of R3 can be described by all linear combinations of two non-parallel vectors, right? If I have a vector pointing here and a vector pointing in some other direction, any linear combination of these two will still be some vector contained in that plane swept out by those two vectors. So we want to come up with a way of describing a subspace, something like that plane, in terms of this set of vectors. You can describe all elements of the subspace as a linear combination of. We call that set of vectors a basis for the vector space. And I am saying this about a vector space, but we want to think of the same thing for a subspace as well. We'll see that you can have a basis for a vector space or a subspace, since a subspace is just another type of vector space. Okay, so let's see an example here. An example of what I was describing there. Any point of the form AB comma 0 really is in the xy plane, right? We have a 0, z coordinate there. And the xy plane will be a subspace of R3. You could show that all the vectors of this form, AB comma 0, form a set that is closed under addition and closed under scalar multiplication, and there is a vector in here, it's non-empty. That means it is a subspace of R3. You can show that pretty easily. But if we take vectors of this form AB comma 0, we can decompose that into a times 1 comma 0 0 plus b comma 0 1 0, right? Multiply this a back through this vector and the b back through this vector, add them together, and you will get ab comma 0. The only point of doing that is that we can show any vector of this form. So the set of all vectors of this form is really just a linear combination of the vectors 1 0 0 and 0 1 0, right? A scalar times one of those vectors plus another scalar times the other. So in that way, we can describe this subspace, the xy plane, as a linear combination of 1 0 0 and 0 1 0. Or we can describe any vector in that subspace as being a linear combination of these two. Okay, so we would like to get a little more detail about what we mean by a basis. Maybe that's a basis. Maybe this set of two vectors here, maybe that's a basis. We need a firmer definition before we can say for sure. So let's go a little bit further. To develop that concept of basis, we will need to develop a couple of things first. It turns out we need to talk about span first of all. Now, the idea of span here is laid out in a definition of vectors v1, v2 through vn span a vector space V. So this is like a verb here. It spans the space. If every vector v in that vector space can be written as a linear combination of these v1, v2 through vn vectors. In other words, if your vector v, no matter what vector v you choose in this vector space, if that vector v is a linear combination of v1 through vn, so c1 times v1 plus c2 times v2, all the way out through cn times vn, for some scalars c1 through cn. Right. In that case, we would say the entire space V can be described by a spanning set of vectors of V. We could describe this set of vectors V1 through Vn as being a spanning set of vectors of V. The other big concept we want to talk about on top of describing span, and maybe before we go further, let me mention this note I have here in the margin here. I'm mentioning that you can use this word span in a couple of different ways. So one way we can talk about it is to say that V is in the span of this set of vectors V1 through Vn. If V can be written as a linear combination of those guys, it's in the span of that set of vectors. The way we're talking about it here is by saying that this set of vectors, v1 through vn, spans the vector space V. So if we use it as a verb, it has sort of one way to be used. You could also alternatively describe span as being a property that a set has, right? The span of a set, like a noun. Okay, so this other big concept we want to describe on top of span, this idea of a set of vectors that you can describe all other vectors in the set, in the vector space as a linear combination of. The other big idea we want is linear independence. And we'll see how to think about this, but let's start with this definition. The vectors v1 through vn are called linearly independent if the identity c1 times v1 plus c2 times v2 all the way up through cn times vn equals the zero vector is satisfied only by having all of those scalars c1 through cn be zero. Right? If the only linear combination of your vectors that equals the zero vector is where all the scalars equal zero, then we say that set of vectors v1 through vn is linearly independent. Okay. Now, if there are a set of c1, c2, all the way out through cn scalars, which are not all zero, so even if you can find a linear combination where just one of these guys isn't zero, then we say the vectors v1 through vn are linearly dependent. So the opposite of independent being dependent. Now that's a kind of a strange definition, even if you have a sense of what linear independence means. But let's look at this note at the bottom of the page to kind of see a way to think about this. The idea is that if you have a set of vectors that are all linearly independent, then no vector can be tossed out of that set and still leave the span of that set unchanged. In other words, no vector in the set can be written as a linear combination of any of the others in the set. If so, you could take a linear combination of your vectors like this up here, v1 through vn. If you could describe any one of those vectors in terms of the others as a linear combination of the others, you would be able to readjust this and express this vector v without that single one that can be expressed in terms of the others. You could replace it with an expression in all the others. So what that does is means that really whatever vector you replaced out there was expendable. You could still describe any vector in your set without that single kind of redundant vector. If that was the case, if you have a set of vectors where you can get rid of one of them and it doesn't change the span, that means you had a dependent set, a linearly dependent set of vectors. Okay, and maybe that'll make it easier to see why this fact here, or why this is our description in terms of a definition of linear independence. Right, I said that really the idea that no vector in the set, down here, no vector in the set can be written as a linear combination of the rest of the vectors. That comes from this definition, or is equivalent to this definition, because assume that there were scalars c1 through cn that are not all zero, such that this linear combination comes out to be zero. Well, in that case, at least one of these guys would not be zero. Say C1 isn't zero. Maybe it's some other one, but let's say C1. Then that means you could move this to the other side, leave the other stuff over there, and you have negative C1 V1 on this side. Since C1 is not zero, you can divide that off and there you have V1 written as a new linear combination of the rest of the vectors. Right, so if a single one of these C values is not zero, and you still get this equation being true, this identity true, it means really one of those vectors could have been written as a linear combination of the others, meaning you had a dependent set, not an independent set. Okay, let's move on to a definition of a basis now. We kind of danced around this, let's get to it. A set of vectors is a basis for a vector space if the vectors 1, span the space, and 2, are linearly independent. Right, so we want to be able to cover the whole space with these vectors. That's what it means to be able to span the space. Any vector in the space can be written as a linear combination of this set of vectors. The linear independence says if we get rid of even one of these from our set, no longer do we have the ability to span the space. Right? We lose some ability to cover our space. So in plain language, let's talk about how we can think about linear independence. For example, if you have one vector in two-dimensional space, right, that defines one direction you can travel in. So linear, any scalar multiple of just a single vector will produce just a line of points. But on the other hand, if you have two vectors not in the same direction, all of a sudden now that allows you to extend out into a different direction into space. Right? You could say those two vectors are independent. They allow you to reach new parts of space. Now, if you throw in these two and you have a third that's in that same plane, kind of played by my thumb and my camera here, then in that case, all three of those sit in that same plane. That third vector, my thumb in that picture, didn't really add any ability to reach any new space. If on the other hand, from here, I added a vector that was kind of perpendicular to the other two, I don't know if you can see my hands. Yeah, there we go. Or just points out of the plane of the other two, then all of a sudden that third vector allows you to reach new parts of space, meaning it is independent from the first two. So that's one way you can think about independence, is pointing in new directions not reachable by any other set of vectors or any other vectors in your set. Okay, so the idea of a basis, though, is that we want a set of vectors to span the space so we can reach everything, and to be linearly independent so we can't do away with any vectors in our set and still span the space. Now, the entire space, the entire vector space that we have a basis for, can be represented by the vectors of the basis with no redundant vectors included. That was the linear independence part. And this concept applies not just to, remember, subspaces are a type of vector space, so this concept applies to subspaces as well. Now let's get into kind of playing with this idea a little bit of a basis. For example, when we describe vectors in Rn, or R3, I should say, let me change this really quick. R3, we use something like an ordered triple, ABC, like this, which can be written as A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. Right? Very easily, you can decompose a vector of this form into a sum of three vectors. And we notice then that any of these general ABC vectors in R3 that we're looking at can really be expressed as a linear combination of 0, 1, 1, 0, 0, I should say, 0, 1, 0, and 0, 0, 1. So that set of those three vectors, since every vector in R3 can be expressed as a linear combination of these guys, that means these guys span R3. And you can show very easily that these are linearly independent, because if you take a linear combination of these guys, like the one I have sitting here, A times the first, B times the second, and so on, if you set that equal to the zero vector, which is what you do to determine linear independence, really, this linear combination equal to ABC, that's the zero vector now over here. And that's the note I've made here. This just implies A, B, and C all equal 0. So the only linear combination of these three vectors that equals the 0 vector is where all three of the scalars equal 0. By definition, we get linear independence of these vectors. So not only do we have that these three vectors span R3, they are linearly independent. The two together mean that this is a basis for R3. The set of these three vectors is a basis for R3. And in fact, it's a very special basis. There are many bases for any given vector space in general, or there can be. This basis for R3 is very specific. This is called the standard basis of R3. And we'll see that out of all of the bases you can come up with, this is actually the most important one for a lot of reasons. We'll see why that is. It turns out we describe many other vector spaces by reverting back to this standard basis in R3. Okay. So let's notice here in R3, we have 3 vectors in our basis. And I mentioned there are many other bases we could come up with for R3. But it turns out every single basis for R3 you come up with would have 3 vectors in it. They would have to. And with that in mind, the fact that any basis is going to have the same number of vectors for a given vector space, we call that number of vectors a very important quality about this vector space. We call it the dimension of the vector space. So the number of vectors in any basis of a vector space is known as the dimension of the space. That's why we would say, for example, R3 is a 3-dimensional space because it takes 3 basis vectors to describe it. Likewise, we could say the dimension of Rn is n. Okay, so we previously saw that solutions to homogeneous systems form subspaces. Take a look back at a previous video for that. Here, I want to find a basis and dimension of that subspace formed by the solutions of this homogeneous system. So if you remember, anytime you have a homogeneous system, all zeros on the right side of your equations, it means that the solutions will form a subspace. So I want to take this system and find a basis for the solution space, is what you can call it. And I want to find the dimension of that. So let's go through this. When I go through this, I'm going to start out just by trying to solve this system. I pack it up into an augmented matrix. Very carefully. And then I start applying row operations. And I do want to stress that you do need to be very comfortable with doing row operations by hand. Here, I'm going to maybe do a couple of them. Let me do maybe the first round of zeroing stuff out. I'll get rid of these 2 using the one that sits above them. I'll take row 2 minus row 1 back into row 2. I'll take row 3 minus row 1 back into row 3. And when I do that, I get first row left alone. 1 minus 1 is 0, 2 minus 1 is 1, 4 minus 1 is 3, 5 minus 3 is 2, 0 here. And it looks like in the bottom row I get 0, -1, -3, -2, and 0. And so check out what happens. I can actually go ahead and, since the third row is just a multiple of the second row, this is going to be very easy to obliterate that third row. I'm going to do row 3 plus row 2 back into row 3. That leaves me a row of zeros, which shows we have a dependent system here. Let me go ahead and do a little bit more. Let me do all that I can here. Row 1 minus row 2 goes back to row 1. That will get rid of this guy because it's above a lead entry. Otherwise, what do I get? 1 minus 3, 3 minus 2, 0. Yeah. Okay, so finally, I have got this in reduced row echelon form, and I want to unpack this back into equations. When I do that, I get x1 minus 2x3 plus x4 equals 0, and I get x2 plus 3x3 plus 2x4 equals 0. Now, what do I do? If you remember from here, to find the general solution, what we would do is identify our free variables, right? Just meaning not leading variables in any equation. So in that case, it's x3 and x4. And express those as just parameters. Let me use R and S. And the idea is we can express x1 and x2. Let me leave a little space here. We can express x1 and x2 in terms of those parameters r and s, in terms of x3 and x4. For example, x1 is very easy to write down. From this equation, just moving everything but x1 to the right side, I get 2 times x3, which is 2r, minus x4, which is s. Similar in this equation gives me x2 as negative, negative 3x3, which is, yikes, negative 3 x3, but x3 is just r, minus 2x4, which is minus 2s. Okay, so what do I really have here? This is what I want to look at now. This is my general solution. But we were asked not just to find the solution, but find a basis of the solution space and describe its dimension. So think of it this way. I'm using column vectors here. You really have choices how you want to express these. But all I'm going to do is make the solutions into a column of these unknown values. Okay, let's see what we can do from there. Okay, well, what we can do from there, remember we are trying to find a basis of the set of all vectors of this form, 2r minus s, negative 3r minus 2s, r and s. So how do we do this? The idea is we want to, in order to get a basis, we want to find a set of vectors such that every vector of this form, of the form in the solution set, can be written as a linear combination of these vectors. That would be a basis, so long as those vectors are linearly independent. So I'm going to split this up into these two vectors. All the stuff with an r plus all the stuff with an s. And now finally, since everything, this vector has an r, I can factor r out of that. I say factor, I can undo the scalar multiplication by r. And the same in the next vector, this guy, pull out the s. And so there we have it. We have found a set of vectors writing that set out. Right? This is a set of vectors such that every vector of this form, every vector that's a solution, can be written as a linear combination. Some scalar r times this one plus some scalar s times this one. I found a set of vectors here that certainly spans the solution space of the homogeneous system. Now, I would have to show that this, in order to show that this is a basis, I'll say it this way, this spans the solution space is the set of vectors linearly independent. Well, for two vectors, it's very simple, but let's see how you would handle this in general. For linear independence, in order to test whether these vectors are linearly independent, remember the idea is that you would have to take a linear combination of them Let's do it this way. Let's write the linear combination in a very leading sort of way here. Make you see what we're really doing. Right, we take a linear combination, some scalar r times one of the vectors plus some scalar s times the other, and you set that equal to the zero vector, which in R4 is just 4 zeros. Now, the idea is you want to figure out, does this, in order to be true, does this equation require that r and s are both 0? So we could say, does the equation r times this vector plus s times the next one equals the 0 vector, does that equation imply r equals 0 and s equals 0? If so, we have linear independence. Well, let's see. Right? This isn't so hard to figure out. All we're really saying here, let's scroll down, is equating stuff on the left side, 2r minus s in the first component, to stuff on the right side, 0 in this component. We get the equation 2r minus s would be 0. The next one would give us negative 3r minus 2s and 0. I guess I'll drop the matrix notation, the vector notation. R equals 0, s equals 0. Right? These are the equations that this actually unpacks to. Right? Every component on the left has to equal a component on the right. There are 4 components on both sides, so we get 4 equations. Well, the bottom two tell us already r and s must be 0. So yes, r equals 0 and s equals 0. So the vectors are linearly independent. Right, and what does that mean? We've already said that this set of vectors here spans our solution space to the homogeneous system we started with. Here we showed that the set of vectors is linearly independent. Therefore, the set of vectors here, let me scroll down even more. The set of vectors here I'm writing them as columns. You could write them as rows. Totally fine. That set of vectors is a basis for the subspace formed by the solutions of the homogeneous system. Okay, so it's a little bit of work to kind of explain every detail, especially when you take this step of taking 2 vectors and trying to show that they're linearly independent. We wrote a lot of stuff out here, but it was kind of silly to do that. When you have a set with just 2 vectors in it, linear independence just means that they're not scalar multiples of each other, right? Because in order for one to be a linear combination of the other, a linear combination involving only one vector is just a scalar multiple. So if you just have 2 vectors, you can just look at them and say, this one's not a multiple of this one, so they are independent. In general, if you had more than 2 vectors here, this sort of process is what you would go through to show they truly are linearly independent. Maybe you can think about why this is going to work out to give you linearly independent vectors when you solve this system. But in case that's not completely clear, we do know the process in general to test a set of vectors for linear independence. Okay, sorry about my voice. I'm a little hoarse from doing videos here. Okay, so I guess I left myself some space to do the work that I did on the right over here. Let's skip that. But let's see another nice example. Are the vectors given here linearly independent? 1, 1, 1, 2, negative 1, 1, 3, negative 3, 0. So this is a good example where it probably is useful to set up a system of equations to determine the answer to this question. Right? You don't just have 2 vectors, you've got 3, so it's not enough just to look at them and say, this one's not a scalar multiple of that one, so they're independent. You can't do that when you have 3 or more. Instead, you have to answer this question. Another way to phrase the question, are the vectors linearly independent, is to ask, does the equation C1 times the first vector plus C2 times the second plus C3 times the third equal the 0 vector? Does that equation imply that C1, C2, and C3 are all 0? Right? If so, we have linear independence. If not, we do not have linear independence. We have dependence. So let's see. Does this equation imply that all the C values are 0? Well, we're going to do the same thing here using rows that I did with columns in the previous example of the previous page. So if I actually add everything together on the left side of this equation, what do I really have? Adding first components, I have C1 times 1 plus C2 times 2 plus C3 times 3. Adding second components, same way, I get C1 times 1 plus C2 times -1 is minus C2 plus C3 times -3 is minus 3C3. And in the last component, C1 plus C2 plus 0, I won't even write it. And this all has to equal the 0 vector. So we just equate the components on the left to the components on the right. And we see that as with so many of these types of problems involving linear combinations, independence, we are really talking about solving a system of equations here for these coefficients C1 through C3. So if I wanted to solve this system, it wouldn't be too bad. I'd pack this up into a little augmented matrix. It's probably the easiest way. Maybe you don't even do this. I don't know. Maybe you see a quick way through this. I can see a couple possible shortcuts. But when in doubt, you just pack up your augmented matrix and start reducing to solve. I'll take row 2 minus row 1 back into row 2. And I'll take row 3 minus row 1 back into row 3. What do I get? 1 minus 1, -1 minus 2, -3 minus 3, 0. 1 minus 1, 1 minus 2, 0 minus 3, 0. And I keep reducing this way. Now, I've done this ahead of time. I will let you fill in the details here. Right, there's going to be some row ops I'm skipping. But when I go through this completely, let's see what I get. Yeah, when I go through this completely, what do I get? I get something pretty definitive here, right? An identity matrix in the left square tells us there was one solution to this. And the solution is where all the unknowns are 0, right? This is my RREF form that this guy leads to. So you can go ahead and fill in the blanks here, take the remaining row ops that you need to take this to RREF form, reduced row echelon form, and you should see the result that I laid out there. And so that means that your unknowns in this system, C1, C2, and C3, are all zeros, or all this column. Right, so are the vectors linearly independent? Well, we showed that setting a linear combination of them equal to 0 implies that all the scalars in the linear combination are 0. That means yes, the set is linearly independent. So let's do another one to end this video. What about this set of vectors? You know what? Before we go to that, I've got an interesting idea that we can play with this previous one with. So I said up here that we found 3 vectors, 1, 1, 1, 2, -1, 1, 3, -3, 0, which are all linearly independent. Let me ask a question. Do these vectors form a basis of R3? Right, we already showed they're linearly independent. But how would you show that this set of vectors does or does not span R3, right? Those 2 requirements, linear independence and span, are all we need to show that this set of vectors is a basis. Well, to check this, we could say, right, in order to show that we have a basis, we need to say that any element of R3 can be written as a linear combination of R3 vectors. So we say any vector V equals ABC in R3, let's say it this way, let's say if any vector V equals, still not happy, let's say if every vector ABC in R3 can be written as a linear combination of the vectors, then what would that mean? It means our V vector is some C1 times 1, 1, 1, plus C2 times 2, negative 1, 1, plus C3 times 3, negative 3, 0. Well, our ABC vector is our V, so let's put that here. And what are we really doing now? We're seeing that what we have to do is solve for C1, C2, and C3 in terms of the ABC. Well, how can we do that? We really unpack this into a system, which tells us C1 plus 2C2 plus 3C3 equals A. C1 plus 2C2, no, minus C2, goodness, minus 3C3 equals B, and C1 plus C2 plus 0 equals C. Right, so if you can solve for the C1, C2, and C3 needed in terms of the A, B, and C vector you've started with, then you've shown that no matter what ABC vector you started with, you can write it as a linear combination of these three. So you solve for C1, C2, and C3, say in terms of ABC. And so you can see, is this possible? Then setting up this augmented matrix for your system. Right, if it's possible to solve for C1, C2, and C3 in terms of the A, B, and C, then when you reduce this down, regardless of what happens to this column, you know you're getting a unique answer so long as this side turns into the identity. And it doesn't really matter. You don't even have to track what happens to the unspecified A, B, and C values, so long as this left square turns into the identity under row ops. You know you're able to solve for the C1, C2, and C3 needed in terms of that A, B, and C. So you would know that, yeah, this is possible, so long as this matrix reduces to the I, to the identity matrix. Right, so it's sort of an interesting problem to say, do these vectors form a basis? Turns out they will. It turns out you can reduce this to the identity, and that, along with the fact that the vectors are linearly independent, that fact would show we have span as well, so we do have a basis here. I thought that was an interesting question to address really quick. So very quickly, let's move on and ask, just like we asked, are these vectors independent, linearly independent? How about these vectors? 1, 2, 1, negative 2, 1, 3, and negative 1, 8, 9. Well, if I set up this problem the same way I did the last one, linear independence requires setting up a linear combination and setting it equal to the 0 vector. Now the idea is to solve for this. If the only solution is where all 3 C values are 0, then yeah, we have independence. If there's any other solution, a solution where not all 3 of them are 0, then you do not have independence, you have linear dependence. So let's try to solve this. I'm gonna kind of skip past writing out this system. I'm gonna jump right to the augmented matrix. Looks like I get 1 times C1 minus 2 times C2 minus 1 times C3 equals 0. Looks like I get 2 times C1, 1 times C2, 8 times C3 equals 0, and 1, 3, 9. And so when I do row reduction on this, the first thing I would do is take row 2 minus 2 copies of row 1 back into row 2, row 3 minus row 1 back into row 3. When I do that, what do I have? 2 minus 2 times 1 is 0. 1 minus 2 times negative 2 is negative 3. 8 minus 2 times negative 1. Oops, sorry, this should be 5. And this should be 10. And 0 here. That's kind of nice, those multiples of each other. 1 minus 1 is 0. 3 minus a negative 2 is 5. 9 minus a negative 1 is 10. This is great. Little row up here. Get rid of this, the third row. And I'll go ahead and, well, let me write it out. And last, I'll scale. And from here, I see this is a dependent system. Maybe that's a hint that maybe this is a dependent set of vectors. Let's see if that conclusion is correct. Also erase this work. Actually, we'll go ahead and take this one step further. I'll take row 1 minus row 2, plus 2 copies of row 2. That'll get rid of this guy above that lead 1 in the second row. 1 plus 2 copies is 0, negative 2 plus 2 copies of 1, negative 1 plus 2 copies of 2 is 3, 0. Okay. And now we unpack this back into an equation, right? This would say C1 plus 3C3 equals 0, C2 plus 2C3 equals 0. Well, this is a dependent system, meaning there are many solutions, not just one solution. You can see that, yeah, when C1, C2, and C3 all equal 0, this is satisfied, right? This equation is satisfied. But what we're seeing is that there are other solutions. Letting our free variable C3 be a parameter, I'll let it be T. Then we describe the others in terms of it. C1 is just negative 3 copies of that. C2 is negative 2 copies of that. So this is valid. This solves our system. For any value of T you plug in. Any real value of T. So yeah, plug in T equals 0, you get that all these coefficients, C1, C2, and C3 are 0. But if you plug in, say, I don't know, T equals 1. Sorry about this, easier. If you plug in T equals 1, what do we get? Well, T equals 1, we get C1, C2, and C3 are negative 3, negative 2, and 1. We could say that negative 3 times 1, 2, 1 minus 2 times negative 2, 1, 3 plus 1 times negative 1, 8, 9 should equal the 0 vector. So we found a linear combination of our vectors where not all of the coefficients are 0, not all the scalars are 0, yet we still get the 0 vector. This means no, these are not independent, these are dependent vectors. Okay, so we've seen quite a bit in this section about bases and span and linear independence. These are really crucial, pivotal concepts in linear algebra. Be sure, if any of it's unclear, we get in touch and we talk about it. Come to office hours or feel free to email. All right, that's it for this video. Thanks for your attention.